All right, so it says Ryan's toboggan is sliding across a level, icy field. So level just means that the height is 0. So we don't have to worry about potential energy. Icy field just means no friction, so we don't have to worry about friction. But there's a velocity of 5 meters. It's a positive 5, so we'll just assume that this perfectly drawn toboggan that Ryan's on yay! It's my artistic interpretation of the situation. 5 meters per second in the positive direction. So if the coefficient of friction, it's already in motion. So what type of friction is that? Well, it's the kinetic is equal to 0.5. How far does he travel before coming to a stop? Oh wait, it's an icy field, but he still has. Okay. I understand what they're saying. He's sliding on the ice, no friction. At some point, he's on the ground, and so this is how far does he come to a stop? All right. So this is a conservation of energy problem. So how do we figure that out? Well, there was work done to get this thing moving, and that's equal to the change in kinetic energy. Okay? Well, what work was done? Well, we have, so really what we're looking for, let me back up a little bit. How far does he go before coming to a stop? So isn't that a distance that we're trying to find? So work, one of the formulas for work is force times distance. And you say, well, what about the force? Well, just relax. We'll get to that. And then, well, what does that mean when we talk about the kinetic energy? Well, the force is actually, well, let me just put it in the formula for kinetic energy. We know that kinetic energy is 1/2 times the mass times the velocity squared. So we can actually, without knowing the force, calculate the force. Because remember that the frictional force is equal to the coefficient times the normal, but also the normal force is equal to m times g. Right? Because if gravity is pulling you down, the normal force is counteracting gravity. So your weight is mg, but the normal force is counteracting. In other words, gravity is pulling this down, which is a negative mg, but the ground is pushing up, and so that's a positive mg. Otherwise, you're going to fall through the ice, you're going to fall through the ground. So what I'm going to do is I'm going to take this whole thing and plug it in for the force. So I have the coefficient times m times g times the distance, and that has to equal 1/2 times the mass times the velocity squared. And then I got to think about this for a second. The frictional force is what slows it down, so that works. But I think I can just divide both sides by this. And then what happens is that the m's cancel. Well, everything over here cancels. But over here, the m's cancel. So I get this formula where the distance is equal to 1 over 2 v squared times the mass of the object times the acceleration due to gravity. Well, we know all those numbers, so we just plug them in. We're going to say 5 meters per second squared all over 2 times the coefficient of friction, and then times 9.8. And that's approximately 2.55 meters. Does that make sense? Okay. Cool, 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 cool.